In this video, we're going to talk about directional derivatives, which will tell us the slope as we go in any particular direction. Now, previously in multivariable calculus, we've seen the idea of the partial derivative with respect to x and the partial derivative with respect to y. For both of these partial derivatives, I would begin by investigating the partial derivative at a particular point x naught, y naught. But the difference was that in the case of the partial derivative with respect to x, I would then only allow x to change. That is, I thought of my y as being fixed at y naught. And when I did this, this two-dimensional surface would turn just into a one-dimensional curve, f of x, where the y was then put in as y naught. And then I could ask the question, well, what is the slope of that curve? And the slope of that curve was just the normal old single variable derivative, as we had a single variable function after you plugged in that the y is equal to y naught. So we got the partial derivative with respect to x. Likewise, for the partial derivative with respect to y, we now plugged in x equal to x naught everywhere. So we restrict ourselves again to a path, and along that path that has a particular slope, and that slope is the partial derivative with respect to y. So that geometrically is what a partial derivative with respect to x or y was going to mean. It was the slope in a particular choice of direction, either parallel to x or parallel to y. But then the question turns to, well, what if I want to take the derivative in some other direction? If I want to know what the slope is, not just going parallel to the x or parallel to the y, but indeed going in any particular direction. This graphic demonstrates that. Down in the plane, I have this purple vector, and the purple vector is a unit vector that's changing the direction where we're looking. And indeed, when I focus on any direction, I go along the curve that's represented by traveling in that direction. At any point, that curve has a slope, and that slope is the directional derivative geometrically. Okay, so that's the idea. That's what I want to capture, but how do I come up with some formulas to be able to compute the directional derivative? And secondly, can I say this in a way that makes it easy to compute in the way that the partial derivative with respect to x and y were both easy to compute? So let's begin with a fixed direction u. I say that I am going in some direction. It's got components u1 and u2. And because I do not care about the length of this, I'm going to demand that the length of u is equal to 1. That is, my slope should not depend on how far I'm going in that direction, just the fact that I'm going in that direction. So I will demand its length equal to 1. Then I'm going to imagine I start at x naught, y naught, and I go off in this direction, which means that I can parameterize my points in the following way. I can say that x is a function of s, and it just says you start at x naught, and then you go in the direction of wherever u1 is, the first component of the vector, you go some amount s in that direction. Likewise for y. Y also depends on some parameter s. You start at the y naught and you go now adding u2 to it, some amount multiplied by s. So as my s increases, I start at x naught, y naught, and then I move along in the u direction. So here now is my definition of the directional derivative. I am going to say that this weird notation, and there's a lot here, but the thing I'm defining is this d sub u of f, or the directional derivative with respect to u of the function f at the point x naught, y naught. Well, it is a limit of difference quotients. In the numerator, what we have is the difference between the function at 2 points. It is the function at the new point, x naught plus su1 and y naught plus su2, the function value at that new point, minus the function value at the original point, the x naught, y naught, and then divided by the change, this change in s that we've made. This is then taking the limit as s goes to 0, and that's my definition. Okay, why did I define it this way? So here is my picture that I'm going to use. The idea is that in the domain, the xy plane, I have these 2 points, an x naught, y naught, and then when I shift that x naught, y naught by just a little bit, a little nudge to the x naught, y naught, that now means it's at x naught plus su1 and y naught plus su2. And then when I make that change in the domain, I get corresponding changes on the graph of this function. So I have 2 points up on the surface, the f of the x naught plus su1, y naught plus su2, that big mouthful, and the f of the x naught, y naught. So I get these two particular points, and from those 2 points, I can put up a secant line. A secant line is just a line that connects 2 particular points that we have on the graph of this function. And so what I'm doing with this equation is I'm really looking at a limit of slopes of secant lines. Indeed, when I go between these 2 points, in that particular direction, you have a rise, the difference in the f values, and you have a run, the difference in the s. That's going to represent a slope, and then I'm going to do as I did in first year calculus so many times when I talked about the definition of the derivative. I take the slope of that secant line, and then I take the limit as my points get close together. In this scenario, the limit as s goes to 0. So this is a very natural definition to give for the directional derivative. Well, this is a lovely picture and a lovely definition, but how do we actually compute it? Indeed, when we were talking about first year calculus, we usually went away from the definition of the derivative, the thing we would often express with the limit as h goes to 0. I'm using s here. And we would have a bunch of derivative rules that would make things easy to compute. And indeed, we have the same story here. Consider the following way of thinking about this definition. Let's get rid of the picture for a moment. When I think about this, the function f depends on x and y. And then the x and y both depend on s. So what I have is a composition of functions. What this expression really is the derivative of that composition of functions. It's the derivative with respect to s of the composition f of x and y, where x and y both depend on s. And then I'm evaluating that derivative at s equal to 0. So this is sort of a shorthand for expressing what we have up at the top. Indeed, when s is equal to 0, your x and y are x naught and y naught. Well, this is a derivative of a composition, and we know how to deal with the derivative of composition, chain rule. So when I apply chain rule to this expression, what I'm going to get is the sum of 2 things. Looks a bit messy, but it's the sum of 2 things, and each of those sums is the product of 2 derivatives. So first, I take the derivative of f with respect to x. I'm evaluating x naught, y naught. And then I multiply by the derivative of x with respect to s, the independent variable. And likewise, I add to that the derivative of f with respect to y, and then the derivative of y with respect to s. This is chain rule. Indeed, the derivative of x with respect to s and the derivative of y with respect to s, these are evaluated at s equal to 0, but if I actually look at how x was defined, when you take the derivative of x with respect to s, or you take the derivative of y with respect to s, it doesn't matter what the value of s is, because one derivative of a linear thing, s goes down to 1. This is just the u1 and the u2. So I can simplify this a little bit by saying it's those same partial derivatives with respect to x and y of the function f, but then just multiplied by u1 and u2. Okay, so my result now is just this, but I'm actually going to introduce a little bit of new notation. For all these weird partials, I'm going to call a new vector, a vector called gradient of f, and this vector is a vector whose first component is the partial with respect to x, and whose second component is the partial with respect to y. This is a vector-valued function, and the idea is that at any input x and y, you get out of it a vector whose components are just the partial derivatives. It's a little bit of shorthand for us, but it's a common one, so we give it this name, the gradient of f. Well, then what we see in this expression is the first component of the gradient of f times the u1, and the second component of the gradient of f times the u2. That's a dot product. When you multiply the first components and add them to the second components, that's a dot product. So here's my final way to write this down. I'm going to say that the directional derivative with respect to u of the function f at the point x naught, y naught finally is given as just a simple dot product. The dot product of the gradient and of the direction vector. Now, the brilliance of this is that one, this is computable. I can do a dot product and I can compute partial derivatives. So this is a very nice, easy thing to compute. And then second of all, look how brilliant this is. The partial with respect to x and y gave us the directional derivatives in the x and the y direction. But then after we had those, after we had just 2 directional derivatives, which we can compute, then to find any other directional derivative, you take the u vector, you dot it with that gradient, and you get your result. All right, well, let's go see an example. So in this example, we're going to talk about a function. It's 2 minus x squared minus y squared, which, by the way, is the graph of the function that I was showing you earlier in the video. I'm going to investigate this at the particular point 1/2 minus 1/2. That's my x naught, y naught. And then I'm going to go in the direction. My u direction is going to be the direction 1 over root 2, 1 over root 2. By the way, this vector has length 1. The division by the root 2 normalizes it to have length 1, so it is indeed a direction vector. The partial derivatives of this function I can do, and I can make the gradient vector to be the derivative of the first component, that's the minus 2x. That's the partial derivative with respect to x. And then the second component, the partial derivative with respect to y, is the minus 2y. And then I take this, I evaluate it at my given point, and I dot it with the direction vector. Okay, so next thing I can do is I can actually plug in my point, and I'm going to get minus 1, 1 for my gradient evaluated at this point. Dot it with the 1 over root 2, 1 over root 2, and that is nothing but 0. Okay, so let's see if we can figure out how to visualize this. In this case, at that point, which is occurring at the value of 1/2 minus 1/2, going in that 1 over root 2, 1 over root 2 direction where x and y are equal, we see that slope, that directional derivative, is 0, and we have this sort of horizontal tangent line at that point. As you'd expect when a derivative was 0, you'd expect a horizontal tangent line. And indeed, if you have some other function, as long as you compute the partial derivatives, going and then figuring out the directional derivatives is a straightforward computation.